Before you begin this lesson, make sure that you can do these warm-up problems. Evaluate the trig function. Pause the video, try the problems, and then unpause to check your work. So, do your responses check out? If no, go back and review evaluating trig functions. If yes, go ahead and move on with this lesson. Lesson 2.03, Finding Vector Components. What are we doing today? We're starting off with a little discussion on the Manhattan distance dilemma. Then we're going to review some old material, and then we're going to learn about finding vector components. Why are we doing any of this? Well, the discussion will help us make some discoveries about distance, and then the review will develop our skills. Finding vector components is the main event of this lesson. You'll learn how to use a new tool, use it to solve problems, and develop your skills along the way. Start off with this discussion. How are straight line distance and walking distance different? Do you think that you could explain this difference to somebody? Click the link in the description to watch a YouTube video by Kyne where she explains the Manhattan distance dilemma. After you've watched the video, do you think that you could explain the difference between straight line distance and walking distance? Once you think you could explain the difference, move on with this lesson. Let's review some notation. We've got components. Vector v has components of 3 and -4. In other words, vector v moves horizontally by 3 units and vertically by -4 units. So if vector v is this dashed gray vector over here, we could analyze it by saying that it's basically moving right by 3 and down by 4. Magnitude, the magnitude of vector v, we show magnitude either with double bars or single bars. Magnitude of v is 5, which means that the sum total distance is 5 units. Vector v moves 5 units. We don't know in what direction, but it's just 5 units in some direction. Let's also review finding magnitude. If we're given the horizontal and vertical components of a vector, we can use the Pythagorean theorem to find its magnitude or its size. So if we don't know the magnitude of this orange vector, we could analyze its horizontal component and vertical component and realize that we're basically just dealing with a right triangle. And we can use the Pythagorean theorem to find the magnitude, or the hypotenuse of the right triangle. But what about the inverse? Could we use the magnitude to find the components? So what information would we need to find the horizontal and vertical components of a vector? We know what to do if we start with this information, but how do we end up with this information? Do we just start with the magnitude and we can get there? Well, let's take a look at these triangles. So if we think of these triangles, which all have a hypotenuse of 5, and we think of their hypotenuses as vectors, well, we've got 3 different vectors who all have a magnitude of 5, but all 3 of them have different horizontal and vertical components. So no, just knowing the magnitude is not enough to determine the horizontal and vertical components. A magnitude of 5 could have a horizontal component going to the right or to the left or a long way to the left. It's just not enough information. So here's the conjecture. Given the magnitude and angle direction of a vector, we can use trigonometry to find the horizontal and vertical components. In other words, if we know that the magnitude of vector v is 5 and its angle direction is -53.13 degrees, we could then figure out both the horizontal and vertical components needed to write the vector in component form. Let's see how it all plays out. Finding vector components. Example. So here's a problem where our task is to write each vector in component form. Let's APEC this thing. Analyze, plan, execute, check. Start with analysis. What do we know? What do we want to find out? What tools could be useful? So analyzing the given problem. Let's see, we've got a coordinate grid, we have this blue vector over here, and this 88 seems to be labeling its magnitude. This red direction angle is 30 degrees. So it looks like we know that we have a vector whose magnitude is 88 and whose angle is 30 degrees. And what exactly are we looking for? Well, we want its component form, so we actually need two pieces of information, its horizontal component and its vertical component. And what tools could be useful to solve this problem? We're going to use the unit circle and trigonometry as our main tools to solve the problem. So let's see. Let's make a plan. How do I get what I want? Well, I want to get the horizontal component. This reminds me of something. This horizontal component, well, isn't that just the x-coordinate of this point? The terminal point of the vector? And when we had a unit circle, to find the x-coordinate at the terminal point of the vector, we just found the cosine of the angle. So this is going to be just like finding the x-coordinate of 30 degrees on the unit circle, cosine of 30. The only difference is this isn't a unit circle, this is an 88 unit circle. This radius is 88 times longer. So what are we going to do? We're just going to do 88 times cosine of 30. Since our circle has a radius 88 times longer than the unit circle, we'll take the rule for finding x-coordinates on a unit circle, cosine of the angle, and just multiply it by 88. So finding the horizontal component should be 88 times cosine of 30. Then what about finding the vertical component? Well, that should be just the same thing, but with sine instead of cosine. Cosine helps us find x-coordinates, sine helps us find y-coordinates. So 88 times sine of 30. Super. So let's execute that plan. First, we're going to do 88 times cosine of 30. Then we're going to do 88 times sine of 30. And we're going to put those in angle brackets to show that they are the components. I'll grab a calculator and calculate these values. And it turns out 88 times cosine of 30 is about 76.21. And 88 times sine of 30 is 44. So we've executed the plan. But was it a good plan to begin with? We should check the context. So do these responses make sense in context? Does it make sense to have a horizontal component of 76.21 if the magnitude is 88? Well, yeah. If we're thinking of the magnitude as the hypotenuse of this right triangle, the hypotenuse has got to be the longest length. So 76.21 being a little bit shorter than 88 makes sense. And 44 being this vertical distance, yeah, that makes sense again. That's the smallest of all three of these distances. And if I'm visualizing this 30-degree angle, then yeah, the vertical component, that vertical distance, definitely looks like the shortest. So I would say that these responses do make sense in context. Sounds like our plan worked. Now let's generalize. How do we find vector components generally? On these screens, I'm going to be showing the specific steps that I use to solve this problem, and you're going to write down the general steps to solve any problem of this type. So it's nice to be able to, solve this problem where we're trying to find the vector components of a vector with magnitude 88 and degree of 30. But you want to be able to find the vector components of any vector with any magnitude and any direction angle. So you're going to describe the steps without saying 88 or 30 degrees, the given values. Let's get started. So for the specific problem, to find the vector components, I set up vector v is going to have some components, this and that. Well, you're going to do the same. Vector v in component form. What I did for this problem, to find the horizontal, I did 88 times cosine of 30. So generally, what are we doing? It's not always going to be 88, and it's not always going to be 30, but it's going to be whatever the magnitude is times cosine of whatever the angle is. I calculated it and got about 76.21. You don't have numbers to work with, so your first component is just magnitude of v times cosine of theta. What did I do next on my problem? Well, I did 88 times sine of 30 to get my next component. I calculated it, and that was 44. You're going to do magnitude times sine of the angle, and that's going to be your second component. I ended up finding the specific horizontal and vertical components of 76.21 and 44, but generally speaking, if we have a vector, we can say that its components are magnitude of the vector times cosine of the angle and magnitude of the vector times sine of the angle. Let's summarize. If you have a magnitude and an angle and you want a vector in component form, what you can do is magnitude times cosine of the angle, magnitude times sine of the angle, and write them together using angle brackets. Vector v has the components magnitude of v times cosine of theta and magnitude of v times sine of theta. There we go. That's how we find the vector components if we're given magnitude and angle.